Hello. Originally for the Kino project, we designed a wearable BLE motion tracker with an accelerometer, gyroscope, and magnetometer. However, for the purposes of Picnic Day and Maker Faire, we had to think of a use for the project where kids and adults could interact with the motion tracker. This is where the idea for Bazooka Battle came from. We took a clear tube and attached one blower fan on each end. Then we placed a ping pong ball in the center of the tube. One person took control of one motion sensor, and the second person took control of the other. With the utilization of the PSOC4, the data of the motion sensors would be sent over Bluetooth to his client via a custom service. The client would then take each motion sensor's data and control its respective fan. The faster the person removed the motion tracker, the faster the fan blew. The objective of the game is to get the ball over to your opponent's side.
Hello everyone, my name is Sergio Villa and part of the hardware team which is responsible for designing and developing the printed circuit board for our device. I'll explain how we designed the schematic as well as the layout for the board. Alright, so this is a schematic for the device that we use for the Bazooka Battle. As you can see, we're using the PSOC4 BLE. We're using a ceramic antenna that's pretty small but has pretty decent range. Since the PSOC uses is reset is active low, I came up with this this button that allows you to reset it on the device itself. I took the same concept to make one for an external interrupt so we can use it for debugging. I even included some LEDs to aid that process. In order to power up this device, we gain the power from a USB or a rechargeable lithium polymer battery. We have an IC that manages all this. We even included this IC that lets us keep track of the battery life that we'll later implement into the phone app. We have this voltage regulator that drops the voltage to a 2.0 volts to power up the processor as well as the sensors. This device has a gyroscope, a magnetometer, and an accelerometer, but since the Bazooka Battle was a side project, we only utilized the accelerometer. And because this is our first prototype board, we included several debugging pins. And this is how the board looks. As you can see, you have the switches, the processor. The sensors are pretty spread out around here, but there's a lot of open space, but this is due to the fact that we were short on time and we weren't really looking to decrease or minimize the area. We also needed space to implement the debugging pin so that we can actually keep track of, see what's connected, make sure nothing's short-circuited. This represents the battery plug that we connect the lithium polymer battery to. As you can see right here is the small ceramic antenna, the USB port. It's the micro USB, so that which is most common for smart devices or smartphone devices. We also have the battery charger and the LEDs for debugging, and all this came out roughly around about $4. It was pretty cheap for 3 boards.
Hi, I'm Kenneth Saisu and I helped create the firmware and the I2C drivers for the device and the 3 sensors. I will now provide a brief overview of how this was implemented. Here we have the I2C driver for the accelerometer. This driver contains functions that implement every feature available for use in the sensor. This includes setting data rates, FIFO buffer modes, orientation detection, enabling interrupts, etc. The core functions from the drivers used in Bazooka Battle were Excel buff read, which is, I believe, right here, and various write functions to properly initialize the accelerometer into its proper mode. And those would be Excel init, which would be initialize, and we have all these write functions here that sets the mode that we need to be in. Here we have the actual program for Bazooka Battle. This is the top design for the server side of things, and here we have the BLE module and the I2C module. And you can also see that we have the drivers that I mentioned earlier, and we are using those in main.c. And you can see here that the driver is being used, and also here we call Excel buff read, which reads accelerometer data through I2C and returns the magnitude of the XYZ data and stores it into sum. And we cast it as a uint8 because we are sending the data over as an unsigned 8-bit integer. And if you go down furthermore, we call handle random data, and what this function is doing is sending the magnitude over BLE to the client. And if you go further down, we see handle random data. It is sending the data over as a notification. So here is the client side, or the receiving side, of Bazooka Battle. And here we look at Kino event handler. This function is receiving the data from the server, and you see right here in Kino value change handle val pair dot value dot val, that is where the data is being received from the server and is being stored as data. And as further down, you see how the fan is being controlled by that data that's being received, and the fan speed is determined by the value of data, and whatever threshold is set, that is what the fan speed is currently set at. And these functions are taken from the provided API from Cypress.
My name is Daniel Lacayo, and I'm in charge of the Bluetooth Low Energy aspect of the Kino project at UC Davis. And I'm going to explain our implementation of BLE. This one is acting as a client, and this one's acting as the server. And they connect through the GAT layer. I wrote a custom accelerometer service where the characteristics of the service are the X, Y, and Z values of the accelerometer, and the two devices connect through the GAT layer, so there's not much going on gap wise other than there's starting of advertising. And for testing purposes, I have the client's green LED on when it's not connected to a device, and I have the server's red LED on when it's not connected to a device. So once I press this button, the client it'll filter through their scan response packets, and when it finds the device it's looking for based on the predetermined hard-coded scan response packet, it'll connect, and it'll connect indefinitely. We have not enabled any low power mode to occur because it doesn't suit our needs for this project. So let's test that. And again, once this is pressed, this should connect exclusively with this, and on the GAT connecting event, this client writes to the CCD of the server, which then enables the server to send the characteristic values to the client using notifications. So it sends it as a notification, and it does so indefinitely, and every time new data is available, it sends it. So now they're paired. This LED turns red when it's connected, and this LED turns off when it's connected. So right now, data is being sent back and forth. You know, the values are changing with the moving accelerometer. And that's Bluetooth Low Energy for the Kino project.
3, 2, 1.
Wait.
Just that little break. All right. 1, 2, 3, go. That's what. Oh, man. That's right.
Shake. Shake as hard as you can. Shake, keep shaking. Keep shaking. You're pulling this way. Probably you want to go back and forth. You want to go this way. Yeah, like that. No, shake it so that you're pulling this way. Yeah, there you go. Keep going. Keep going. Keep going. Keep going. Up. Up. And forward like this. Shake it harder. Shake it.